Hello, everyone. Welcome to our beginner-friendly system design series. So before we get started, as usual, I just want to give you a brief overview of the series. So the goal of these talks is to help you get started with system design on real life app examples. And during each event, we'll talk about how to build a certain app from scratch from the system architecture perspective. So you will not have any coding, just conceptual overview and walkthrough. And also, each event is going to have 5 core app features we will discuss. So today's event is called How to Build Google Meet from Scratch, and we'll talk about its 5 core features. So real-time video and audio streaming, number one, scalability and multi-participant management. So probably we'll spend the majority of the time on those two. Then screen sharing is feature number 3. The next one is real-time chat, reactions, and meeting controls. And the last one, caption and summary generation. Also, we will pause this series after this event just because we are planning our Google Dev Fest. So Google Dev Fest is our yearly AI conference that we'll host on Saturday, October 26th. So if you happen to be in the Waterloo region or if you want to travel, feel free to attend. I'll share the place where you can purchase the tickets in the chat. And also, as usual as well, I want today's session to be as interactive as possible. So feel free to drop your questions in the chat and we'll answer them live. But now I want to introduce you to our today's speaker, Victor, who is a Google developer expert in cloud. So thank you so much for joining us today, and take it away.
Yeah, thank you so much for having me. It's it's a pleasure to do these things, and it's always fun. And first of all, I want to preface this by saying I have no real experience with Google building something like Google Meet, but I have built a lot of web infrastructure, cloud infrastructure, and the way I approach these things is that it's kind of like physics. If you're building something, even if you haven't done anything in particular like Google Meet or real-time video streaming, if you understand the physics and the engineering around it, you can kind of box things around and understand what the constraints are and what components are necessary. So that's kind of how I'm approaching this. And so maybe I'll make some mistakes, but that's okay. I think we're all here to kind of learn, and hopefully we'll walk through it and figure out how somebody would go about building something like Google Meet.
Yeah, and I guess the disclaimer is that, it's not the exact replica of the actual system. It's just one of the ways how you can build it. So yeah, definitely.
Yeah. So just kind of a really quick introduction. So I'm Victor. My day job is I run a company called cloudkite.io. We build Kubernetes, a lot on GCP. Thank you, Google, for doing the GDG series. But we also work on other cloud providers like AWS and Azure. So that said, I think anytime we are asked to build something, especially when I do this in my day job, we kind of have to go back and try to figure out the simplest possible thing, right? So if somebody came to me and said, hey, let's build a kind of a meeting platform like Google Meets, I would go back to first principles and I say, well, imagine the simplest scenario. This is like 2 users, right? So we have user A, laptop here, and then user B, right? And so in a scenario where we're just building for 2 users, like what is the dumbest, simplest thing that we could possibly do? Well, these laptops have cameras usually, right? And so a lot of cameras, maybe not the laptop cameras, but a lot of like USB cameras that you can buy have the ability to get an IP and stream directly. They run a little web server inside their controller, and they run, they can stream, right? So maybe that's one way to start, right? And so if I do like a camera, you don't even really need a laptop in this case, right? Like I just have a camera, and then it exposes a stream, and it uses a protocol called RTSP, I believe that's what it's called. And so the laptop itself gets an IP, or sorry, the camera itself gets an IP address, and it's just listens to a port, and anybody can subscribe to it, right? So this let me zoom in a little bit so we can see this better. So this thing has a RTSP stream, right? It's just capturing information over here, exposing a server, and it's just streaming. So I can easily, let's say this IP address is like 1.1.1.1, and I don't know the RTSP port, but let's just call it like 3000. So my friend over here who wants to watch my stream can just use any RTSP viewer. Could be like VideoLAN, like VLC, if anybody's familiar with that. They use a cone icon for some reason. And so then, if you have the VideoLAN application, you can literally just put in this IP address, something like RTSP, this URL, and watch this stream, right? And then we can do this in reverse. So my friend who wants to also share their stream can do the reverse. And we go here to this laptop. Hold on a second. Go here. Oh, that didn't work out so well. Like this, right? This IP address could be like, let's say, 2.2, right? So I'm watching this stream that my friend has set up over here, and my friend is watching my stream, and so this could possibly work. RTSP is going to stream video, it's going to stream audio, or whatever codec that VLC handle that the server has, and VLC is pulling in the data.
And also, just to clarify, so the cone that you put in there, it's the video, the application that plays the video, right?
It could be anything, right? Thank you, Alexander. It's I just happen to be familiar with VLC, and I think there are plenty of media playing applications that can play a RTSP stream, right?
Mm-hmm. Yeah.
So this works, maybe. What are some potential problems with this, right? Well, one problem I can think of is that this is streaming audio and video, and it's playing out of my laptop, right? There's audio and video, and so the video I can see on my screen from this camera. The audio gets played through the speakers, and it gets picked up by my camera who's streaming to my friend. And so we create this like feedback loop. So this is like a homebrew. How do we do the simplest video streaming between two participants? We had some audio issues, right? And there's no control. There's no anything nice that's in Meet that we want to use. So while this works, maybe we have to do something a little bit more sophisticated if we want to have a product that people actually want to use, right? So let's scratch this.
Also, before we move on, just a quick question in the chat. So is there a limit on the number of requests handled by the cameras? And I guess, how does it handle traffic, like generally?
I mean, the limit is really going to be the processor on the camera, and they're going to be little microcontrollers. They're not going to be that strong. You're going to have some bandwidth issues, so based on a little web server that's running on side the camera, like how many streams can it handle? from a CPU and memory and network perspective. And the real issue is that the camera probably has an internal IP address, right? And so if it's on your local Wi-Fi network, it's going to get assigned a DHCP address, just like your computer. And I won't be able to give that IP address, the internal IP address, to a user over the internet and expect it to work. And that kind of goes into my next point, right? Like, really, for something like video conferencing and meetings, you have to have computers kind of talk to each other. And so how do you do that, right? And I'm going to kind of draw that out a little bit, right? So my computer here, let's forget about the IP camera. Let's give my computer this IP address. This is a internal IP address. This is how most computers would work these days. And this is like, actually, this is internal. So let's call this, let's say 192.168, because that's a very common one that home routers use, 1.1, right? And then this could be like internal of 172. This is another range, 16.0.0.1 or 0.1, okay? If my computer wants to talk to this computer at this IP address, it won't work because these IPs are non-routable IP addresses. So what typically happens is you have a router at home that looks like this, right? And then your ISP assigns this router a public IP address, so like let's say 1.1.1. Your friend has this as well, 2.2. And then, so when I get to the internet, what ends up happening is I make a request to, like, let's say the internet. This goes out like this, and the web server sees a source IP of a request from 1.1.1.1, okay? So this router here, what it does is it maintains a NAT table, right? So it says, so when my computer makes this request comes from, let's see, this is not actually a table, give me 1 second. So it maintains a NAT table. So it's like source, IP, port, source port, and then external port. All right. So my router maintains this table, and source IP could be like 192.168.1.1 because there's going to be multiple users, right? There could be another laptop on here that's .2, right? So in this case, I'm coming from .1, and my computer opens up a port. So it's going to open up some random high port, let's say like 30,000. And then when it gets to the internet, my router says, okay, I'm going to assign some other random port, like let's say like 40,000, right? So then when the request comes to the server here, it actually sees it coming from 40,000. Okay. So then when the request comes back, it goes here, and the destination is 1.1.1, 40,000, and then my router here maps this back and sends the request response from the server back to this IP at 40,000. Does that make sense?
Yep.
And so because IPv4 public IPs are limited, pretty much we're all using NAT with IPv4 these days, and these home routers are all designed to do that. It becomes a problem when we want to share data from one computer to another because there's two laptops behind NAT gateways. So some smart people came up with some ways to around this, and what people have ended up building, because when we're doing video conferencing, then between two people, between a handful of people, we want to do things the simplest way possible, right? And so we don't necessarily want to put a server in the way. So if I'm streaming, my video feed from one computer to another, really we want to make a direct connection, right?
Mhm.
So, but because of that, we can't just make a connection to each other. But we have what's called a stun server, and this stands for let's see, Session Traversal Utilities for NAT, something like that. And this is like you can think of it as like caller ID, or like a mirror, right? So what happens is when let's say we write a client, we write Google Meet. It's a web application. My browser starts Meet, and I start the call. I'm the only one on it, and then I add my friend, right? My friend joins Meet. So this is Meet, right? So I talk to Meet, and my friend joins Meet as well. And what ends up happening is that my Meet application on my computer sends a request to the stun server and says, what is my IP and port, right? And so and the stun server responds back to my Meet client sitting over here with my IP and port that I'm exposed to the internet as, right? And so now that means that requests or packets that come from the internet that are destined for my public IP on that port make it back to my Meet client on my machine. Yeah.
Mhm.
That makes sense? Or is that confusing?
I think, would you be able to repeat that again? Yeah, I think it generally makes sense, but
yeah. So let's do stun steps. Sorry about that. So maybe the first thing we need to do is, I have a Meet client on my browser, and I need to share my IP address to another Meet user so that we can make a direct connection.
Okay. Yeah.
Most efficient, right? And so in order to do that, my client talks to a stun server. So the stun server responds with the public IP address and port that I'm appearing as on the internet. Okay. And then step 3 is then Meet, or my client, video chat or client, can now tell other users what my or how to send data to me. Yeah. Right, and that goes through the NAT table, right?
Yeah.
So if I do that, Meet is just sitting over here. Like, let's just say it's an application on the internet. It sees like this is a Meet participants. So this could be like user 1, public IP address of 101.1.1, on port 5000. and then user 2.2.2 on port 6000. And then, so now Meet has this metadata, right? Like this is, it knows about these users. And so Meet tells this user to talk to me directly. Really, it should come from the router here. Send video to 1.1.1 on 5000. And then my router sends video here, send video to 2.2.2 on 6000. Okay. So now we've solved the ability to have two participants. Using a simple application. What happens if we add in more users, right? Like we added another user over here, and this guy is like 3.3.3, and so on and so forth, right? Like we could still scale this, to like maybe a handful of users, but every time we do this, each of the participants has to make a direct connection to each other. It becomes like a mesh network. And I think this works. I think probably Google Meet does something like this, as well as like all the other things when you have a small number of users. And you want to ask like why why would you do this instead of having everybody go through a central server? Well, if everybody goes through a central server, it may not be the most efficient thing, right? Like if the server happens to be in like US West Coast and all the users are in the US East Coast or in Europe, is it most efficient to have everybody's packet go to the West Coast and then back to the participants? Or is it better to have the users communicate directly to each other? And I think for video, where having low latency and responsiveness is important, having users talk directly to each other is probably better. So, so for a low number of users, a mesh network is probably better.
Yeah. So maybe one quick question. So can we quickly go through a process of, for example, when a user joins a meeting, right? So how would this table, like Meet participants table, be updated? So the assumption is that, since like you were saying that technically the packets do not go like through a server or whatever, right? They are connected directly. So where is this table kind of stored of Meet participants?
Yeah, so I would say like meet.google.com. This is kind of like a metadata server, right? And so this meet.google.com that everybody's talking to would maintain this information. It's like kind of the coordination server. But in this, for a low number of users, you don't necessarily need this server to handle all the video streams.
Okay. So essentially, it just like pings, like hits an endpoint, like to kind of connect, let's say, right? Then the IP address gets added here, and then the connection gets established.
Yeah. So I go to meet.google.com, well, there's a couple things. Let's step back a little bit, right? If you look at a Google Meet URL, it looks something like meet.google.com/ like some random things like that, right? Like, and so there's a couple things that happens here when your browser goes to this URL. Maybe their first step would be, first of all, you load the Meet client in your browser, send some cookies, and then Meet determines if you who you are you logged in. So maybe this is like a off step, Okay.
Mhm.
And then if you're logged in, are you allowed to control this meeting? So, sorry, when I say auth, this is authentication.
Yeah.
And then here, I say auth is an authorization, right? Are you the owner of this meeting, or are you a guest? Are you the owner, guest, right? And so you've probably seen this when you log into Meet. If you're not logged in at all, you don't have any Google cookies set, you'll get redirected to log in, right? And so then you log in, and if you're the meeting owner, you just instantly enter the meet. If you're not the meeting owner, and so we go to step 3, are you a guest? And if you are, you're already, because you've been added to Google Calendar, you'll just get logged in. And if you're not, you can join the meeting because you've been authenticated, but you're not authorized. And then the host or the owner of the meeting gets a little pop-up that says, you want to allow
Deny.
Yeah. So and these things, we can kind of talk about how those work as well. Here, I'm gonna actually.
I think we can take it for granted, maybe even just because. I think those it would be, as you said, like those first filtering steps or whatever, like authenticating, right? Then making sure that you are allowed to access the meeting, like being admitted or denied access to the meeting, and then makes sense. I just was wondering like how the initial connection is set up, right? Because we have this table, but I think you answered my question in terms of like where it's stored and how it's all managed now. So
we've kind of only talked about so far as a transport, like a network layer, like port IPs and ports. We haven't really talked about the protocols, whether it's like what kind of IP protocol it is, TCP or UDP, and then even like higher level at the application side, how Meet handles things like low bandwidth. Like maybe some of the users have higher bandwidth than other people, right? So I think I wanted to make sure that we understood how getting the packets, the physical packets from one machine to another works usually, and then we can kind of go through and go up the stack to the application layer.
Yeah, definitely. I think the networking overview was great. It was very helpful. So thank you for doing that. And so basically, like this is, let's say, V1 of the app, right? Where it's, as you said, only a couple of users. And as you mentioned, it wouldn't, like in this case, would it go through this Stan server or no? Like, because
I mean, I think if user 3 is like a really fancy user and they plug in their computer directly to the internet, and they have like 3.3.3, then there's no reason for them to go through a Stan server to let the other participants know their public IP address. They can just the other users can just directly connect to their IP address. You know what I mean? So it's something like this, right? And so this guy doesn't, I don't know if you've ever plugged you can configure your laptop directly into your home router, your ISP, and get the public IP address instead of using a router, your personal router, if you wanted to. And you were directly connected to the internet, like all packets to that IP address end up at your laptop. And then you're not using that anymore, right? Or maybe in the future when everybody moves to IPv6, we wouldn't have the need for NAT anymore, because there are enough IPs for every device to have a public IP address.
Basically, more and more so it's like a net, basically, right, of different connections. So the server is not participating in those. It's basically just hitting this meet the google.com, a new connection is created between the devices, and that's it, right?
Yeah, I think in this scenario, I would consider meet.google.com as like the coordinator, right? And so every participant, they have to go through these steps. And then Meet says, okay, we only have 2 or 3 participants. Here's Alexander's IP address, connect to him. Victor, here's Victor's IP address, connect to him. And so they're just kind of the coordinator. And then, we would call this like a mesh network of participants.
Okay, makes sense.
Yeah. So
now if we want to scale it, right, and like add, for example, if we want to have 50 or like 100 participants in the call, how would it work?
Yeah. So as you scale things, you run into issues, right? And like I think even if you go look at like what there are limits to how things work, right? So I think if you even Google, right? They have like limits on the number of participants, right? And so, and then there are technical reasons for this, and there are business reasons because they want Google also wants you to pay higher plans to have like more meeting participants and things like that. But let's say at some point the mesh network doesn't make any sense, and that number is probably pretty low. I would probably less than 10, right? Like at some point, you don't want to stress each individual participant. If I have to maintain and then do all the video encoding and decoding for everybody on the call in my Meet browser, like that browser tab is going to go nuts and use up all my CPU. So you hit a good point. So maybe at that point, what would happen is, there'd be like meet.google.com would run, let's have different components here. So this is like, let's just call this the coordination server, right? And so, and then they might have another server that's it's called a multi-point control unit, typically, based on my research, MCU, multi-point control unit. So what happens then is my browser does a couple things. It captures my video and encodes a stream. And then from the coordination server, it would tell my browser what to do. Tells Meet client what MCU to send data to. And then my browser, instead of talking to users directly, it would send the video stream to the MCU, right? And so there's a lot of nuance here. My browser has to figure out what the optimal like codec is. Oops. It has to be compatible, right? My browser, if it sends like some codec that the MCU doesn't understand, that obviously it won't work. So like using agreed upon video and audio codecs. And then maybe the MCU handles, well, actually, the protocol will handle things like congestion control, right? Congestion control, etc. So, and so it, and then this is a we'll have participants over here, and there's a difference between like a YouTube stream and a interactive stream, right? If it's just like a YouTube stream where like This is the producer of the video.
Yep.
All this MCU has to do is just send data. It's just streaming like a video, right? And it's super simple.
Yeah.
And with this, you can scale, as much as this particular server can handle, right? Like from a network perspective.
Mm-hmm.
This, there's a little bit of complexity here in that maybe this is like a phone and it has like a low bandwidth, right? And then this is like, high bandwidth, right? And so the MCU, its job is to kind of figure out between all of the consumers, what their codec capabilities are. Let's say this is like VP9 from Google, and this is like, like H264 or something like that, right? Depending on the operating system of the browser and things like that. So, for a stream, this creates the data and sends it here. All these clients, when they talk to Meet, they were told to talk to this MCU and download the data, right? So this works. This works great as long as you have a single MCU.
Mm-hmm. Right. Also, just maybe to clarify, so coordination server, it's clear. So basically, it's a server. Then browser and MCU control unit. I'm just a little bit confused. Like, why are they connected to multiple machines? Like in this diagram. So so this browser and MCU, where do they live?
Yeah, right. Yep. I'm sorry. So this is like my laptop. So this is like my local connection.
Yep.
To back, right? This is me.
Mm-hmm.
And then this would be like Google data centers. Something like this. Yep.
Mm-hmm, mm-hmm. Okay, and then the other computers are just the other participants, basically.
Yeah, this is like.
Okay.
Yeah, this is just like over the internet.
Okay, makes sense. Yeah.
Yep. Something like this, right?
Yeah.
Yep. So at some point, like maybe this particular MCU gets overwhelmed, right? And so, or maybe this is like in US, and so all these are all like US users. But if you have participants in like a different in the EU, for example, you might have a separate MCU for the EU. And this would be you would call something like this like a cascading stream. So like the MCU would stream from the US MCU for all the US users and send it to the EU, and all the EU users would be sent here. And the coordination server would tell when these clients connect to meet.google.com. The coordination server would tell these clients to go to this IP or go to this region for your source of your stream, right? So the MCU's responsibilities are accepting streams from clients. It would do things like encoding various encoding output streams based on clients support. And what else could it do? Yeah, I mean, those are like kind of the base things that you would expect an MCU to do.
Yeah.
And there, there could be scenarios where users fall behind, right? Like if a particular user has a low bandwidth situation, like their stream maybe ever like gets slower and slower over time. So the MCU would basically tell users like, hey, like drop a bunch of frames in the video to catch up.
Okay.
Right, so that people are like in sync, because it would be very weird. Like we've all had calls where you talk and then there's like a weird delay, and then the user responds because there's a big delay, and that's because for latency reasons. And so the MCU is trying to minimize all of that.
Okay. So basically, I actually had a question. So for example, right, my camera resolution or whatever, right, it's pretty good. So for example, the video quality is great, but then when it's streamed or whatever, like this connection is established and my video is streamed to another user and their computer cannot handle it. So basically MCU would be responsible for like reducing that resolution and sending them the...
Yeah. So I want to go, we kind of skipped a couple of things. There's a whole protocol called WebRTC that was developed, I don't know when, but it was developed to kind of handle this type of thing, right? So probably Meet uses something like that, or or enhanced version that Google has created. So like what WebRTC would be typically responsible for is actually probably the mesh stuff. Like initially when you're connecting in the WebRTC protocol, there supports mesh. So like MCU would use this. It is also responsible for coordinating the codecs. And it has support for data channels. So data channels would be text messages, like files, screen share. No, not screen shares, because screen shares we go through video. Like text messages, files, stuff that's not part of the video stream. And it supports the handling stun and turn. I actually forgot to talk about turn. Stun is how we discover each other, but there's also turn. So I want to go back to here. There are some cases where like users have very restrictive firewalls, and even though you use a stun server to get your public IP's port, the response coming back would get blocked by your gateway, right? Your router. So basically, what happens there is it's just like a giant proxy, right? Like users would have a sorry, my thing is getting quite messy here. We would have a turn server, which is like a proxy. And the users, instead of connecting directly to each other, they would end up going to the IP address of the turn proxy. And all that's doing is just like providing a public gateway where everything flows through.
Okay, makes sense.
And so WebRTC as a real-time communications protocol supports all this, and all the various steps of establishing a connection and figuring out what the codecs are. And so what's interesting is that like within within this entire process, there are things that are very very important to send, like the coordination data, chat data, And so this uses TCP because, like, imagine, so TCP, the nice thing about that is your data is more or less guaranteed, right? TCP data is ordered. So the packets are ordered. You know that, when I type a message, it comes in the right order. It's not out of order. Excuse me.
Good.
Data is reliable for the most part, because if a packet is dropped, it gets resent. And so really quick on the other side of things, that protocol that people use is UDP. And so UDP is not guaranteed, not ordered. But the benefit is it's low overhead, and so therefore it's fast, right? In video, does it really matter if I drop, the data that you send to me with your video stream loses packets? Not really. What we care about is being real time, right? So video streams are generally UDP based, because if I'm on a cellular connection and my computer drops for a bit, what matters is the next frame is not the frame that I missed, but the frame that's closest to real time. And which is kind of the opposite for the chat messages, right? Like if you're typing, a couple sentences to me, and I drop connection, what's important is that I get the words in the right order, not that the words arrive, right? And so, in WebRTC, there are like the data channels. It sets up the connections using TCP, which is persistent and ordered and reliable, whereas the video and the audio uses UDP.
Yeah, I think that, there was just I guess for a general overview, I was just wondering, how this resolution or whatever coordination happens. But I think there are a lot of complicated steps that that are done on that side. So yeah.
I mean, the other thing is, like, I'm kind of simplifying quite a bit, but like maybe the MCU, one of the things that it would do is, it takes in a video stream from the source, from my computer here, right? And then it outputs various qualities, right? So it could do like one box could be like VP9 4K, right? And then the other would be like I don't know, H like 265 at 4 at like 240, right? Like resolution. And so these could be these would be options available, right, at different addresses, right? So the MCU would output this, and then users could choose. Let's say they started off at home, right, on their, and then they are downloading the stream from this 4K resolution, and then they switch to their phone because they get in the car, right? And the phone's like, well, I can't handle this, so because I'm on a low bandwidth, I'm going to switch to this stream instead. And it could come from the same MCU.
Okay. Yeah, makes sense. So basically, if we like zoom out a little bit, so we talked right now, right, how the basically one user streams their video and audio to other participants. So does it, and what about the other way around? So it's basically the same process, but on other computers, right?
Yeah, exactly. So the kind of the coordination server and the MCUs kind of all tell the clients, like, each one of these things is running the Meet client, and they're also all, I'm going to get rid of this cloud here. They're also all sending their streams in. They're sending it into this MCU as well, right? And so and so the MCU is constantly encoding and decoding things. And one other big benefit of an MCU is that you have multiple users sending data to it, and so instead of I'm going to actually do this on another page. So you might have multiple users sending data to an MCU, right? Because they're all sending video, right? Mm-hmm. And so instead of having the MCU send two separate streams to this user here, this is user 1 and the user 2, and instead of doing this, it would send a single stream that has 1 plus 2, or as many users as it needs, right? So it combines the streams into a single one, and would, instead of saying the full 4K that this user is seeing it in, transcode it down to like a little tiny stream that has multiple users in it.
Mm-hmm. Also, we talked a little bit earlier that there is like a limitation of 100 people, right, or on Google Meet. So is it basically because MCU can handle up to 100 connections, or it's multiple MCUs can handle up to 100 connections, or like what's the reason for that?
Yeah. I mean, like I said, partially it's a business reason, because like Google is trying to get people to pay more for different, like workspace Premier or Premium or whatever it's called, right? And they have different limits. Yeah. But the business decisions get driven by technical reasons as well, right? Mm-hmm. The simplest possible architecture is just to have a single MCU.
Yeah.
Because distributed systems are hard, right? Mm-hmm. If you have this and you have like in the EU, and you have this in like Africa, right? And some users are like down here. And then you have to coordinate these, this thing has to coordinate this thing. There's this kind of data going around everywhere. And every time you add one of these things, it's additional complexity, additional latency, right? And so it costs Google money, right? In engineering time to make sure that all this works and the networks are fast, and so the less complex systems are, the cheaper they are to operate.
Yeah, makes sense. Also, there is like, I guess, a question / thought in the chat. So basically, so there are like a few messages, so I'll try to condense it into one. Sure, yeah. So it could, so the comment is that basically the solution can look good on paper, but might not work in the real world. So is it correct to say that to do system design, you need one of the following: either to know the topic really well or do some extensive research beforehand? So yeah, I guess this is a general, I guess, comment. I think like even when designing this system right now, we are skipping a lot of things, right? It's just a very high level overview to familiarize yourself with the concepts and just to understand generally how the system operates. But I think so the other comment is right, that when you're actually, I guess, if you were at Google and you would need to design a system like that, obviously it would be like months of work and a lot of testing and proof of concepts and just reiteration and finding, I guess, the best approach to take. But yeah, do you have any comments, Victor?
Yeah, no, I think that's absolutely right. Like, I've in my career, I've designed things that when I've asked to do things that most of the time it's like, especially early on, it's like this is the first time I've done this, right? Like to kind of give an example, um, you know, uh, 10, 15 years ago, I was a backend engineer at a company, and we were using big solar clusters, right? And so every time we changed the schema for our solar cluster, we would basically have to re-index everything, right? And if the indexing, our data size was multi terabytes, and so it would take hours and hours, sometimes like over a day, to re-index all the stuff into our from our database into the new schema in Solar. And we couldn't be offline for like 2 days while we were running indexing. So one of the solutions was we would spin up a bunch of EC2 machines with a new Solar schema, run indexing offline while the old version was still serving the internet, and we would create the index. And now we had this problem of, we had, let's say, like 2 terabytes of Solar indexes on disk that we would need to distribute to the live servers that were, in the same data center, but we needed to copy. Let's say if it's 2 terabytes, you had to copy it times the number of servers that existed, right? So like maybe we had like 10 servers. So like 20 terabytes of data copying over at the time it was 1 gigabit network still takes forever, right? And you would get bottlenecks on the source of, like the source where the server, the data existed, was still a 1 gigabit network. And so like, how do you quickly copy all this data across all the Solar servers? And so like, when I was asked to solve this, I had plenty of experience with Solar, but I'd never had to deal with distributing like massive amounts of data in as short time as possible, right? You wanted to minimize any outages.
Yeah.
And that's when you start experimenting, right? To go back to the original question, like, you just do the silliest thing, which is like run a bunch of SCP commands, see what happens, and it takes forever, right? And so then you iterate over time, and then you start learning more things, right? You start learning what the bottlenecks are. It's the network cards, it's the disk, and eventually, what I ended up doing, which I had no experience prior, was using BitTorrent, right? Like I realized that if I wrote a BitTorrent client that ran on each of the Solar nodes and had a script to kick off the transmission, as each Solar server grabbed some of the index files, you would be able to share, and parallelize the transmission from, first this one, Solar node to like, and then as they each populated their indexes, they got faster and faster and faster until we were able to saturate all of the network cards on all the machines at the same time. And it didn't matter that the source machine was only 1 gigabit. And that's something you do just over time, right? You experiment and you learn.
Yeah, definitely. And I guess as more feature requests come in, the system design can change like completely or at least partially, right? So yeah, and I think so. There was another comment like saying that. So yeah, basically, I kind of agree with that. That this is more like of an exercise, right? And something that you could potentially say on the interview, right? Since whenever you're being interviewed, right, you don't have a lot of time. This is basically like a condensed version, right? Where you could just show that you know those concepts and that you know generally how the system works. So would it be correct to say that this is like basically an interview simulation of the question, how to build Google Meet?
Yeah, 100%. I mean, it would be a disservice to the people who built Google Meet to say that they're able to build it in like an hour or 90 minutes, right? Like,
Yeah,
I'm sure this is like decades of man hours from very smart people at Google to make something as reliable and easy to use as Google Meet, right? And so that goes from like there are some, Google Meet is a browser-based client app, right? And so there's tons of super smart people working just on the browser components. There are people who work on the infrastructure, people who work on the backend MCU code, right? And so it's just like the complexity is like immense.
Yeah, makes sense. Cool. I think basically, like right now, we covered like this scalability portion, right? Maybe I guess one last question. So MCU in a nutshell, is it also a server basically, or it's something else?
Yeah, it's definitely a server. You can I treat them like kind of as black boxes, but
Yeah.
you're right. It's a server, but it could have specialized hardware, right? Like that is, could be designed to be very good at video encoding and audio encoding.
Okay.
Um, and you don't necessarily need that for the web server that runs like meet.google.com as the coordination server, but the things that actually need to process video can become pretty heavy, especially if you're having to output, a dozen different stream types for different clients.
Okay, makes sense. And maybe one last question about MCs. So like on the backend, right, you can have microservices, right, or whatever that can be like that can have like multiple instances of certain things. So is it applicable to MCU as well, where you kind of have multiple instances of the same MCU server, or just to handle more traffic, or no?
You could, right? We have it here as geographic delineations, but you could easily have it as like capacity delineations, right? So, you can have, a bunch of servers in the US because maybe that's where all of your users are connecting from, right? And so your, your coordination server could send these users to different MCUs, but the MCUs all have to talk to each other, right? And in the same way, right? And so like every time you do that, it adds a little bit of latency and a little bit of complexity.
Yeah, makes sense. Because I was like, yeah, if you split, like create multiple instances of MCU, and then one user connects to one and the other to a different one, then how do you combine those streams into a single, like how we have it on the diagram, like 1+2? How would it happen like with multiple MCUs? But I guess you just mentioned that they would communicate between each other. So yeah, that makes sense. Cool. Great. I think let's move on and quickly discuss maybe screen sharing. So I guess from my personal experience, what I've seen is that when you share a screen, it seems like it's another participant gets added to the stream. So is that basically one machine would stream two videos at the same time, or how would it work?
Yeah, so that's exactly right. So let's say your operating system has APIs that your browser via Meet talks to, and so when you share a screen these days, you'll usually get a pop up that says, "Do you want to share the whole screen, a window, and then maybe even a tab out of a browser," right? And so those are APIs exposed from the operating system to securely allow applications to read screen data, right? Because you don't want any application to read any screen data and send it to the internet, right? And so like one of these would be like your video, right? Your computer, if you establish a stream, could have another stream to the MCU, which is like your screen sharing. And so the MCU's job in that case is to offer these streams as options for users, so like or viewer, right? So the client may choose to like watch, look to see like Victor plus Alexander's screen or something like that, right? And so that might be two different streams, or it could be a single stream depending on the MCU. So the MCU is responsible for kind of collecting all this, re-encoding it for all the clients, and it's just the output it's all dependent on the client, because phones are different than browsers on the computer.
Okay. Yeah, makes sense. So basically, yeah, MCU's job is to adapt to the receiver in this case, right? So the client, as you said. So
yeah,
cool. Great. I think also, yeah, we can quickly cover like real-time chat reactions and meeting control. So I know that we briefly talked about chat already, right? But I guess in terms of like reactions and meeting controls, I feel like, so by reactions, right? If you like put a like icon or something like this, basically it's like a chat as well, right? But just a different symbol is displayed instead of text.
Yeah. And so that maybe, in this case, like maybe the coordination server is perfectly capable of doing that, right? Because it's going to be low bandwidth, right?
Yeah.
And so maybe when we here, let me put this box here, because I know it was confusing as to like what was Google and what was not. Like, so we're going to call this Google, right? So this coordination server, like maybe you would send your chats, like emojis, chats, and things like that to here. And then so the everybody would pretty much be talking to both the coordination server and an MCU, right? So they would typically use something like an MCU for the video and audio things that require a lot of transcoding. And then for everything else, you would use the coordination server or application server. I don't know what you want to call it. It's just kind of a logical box.
Yeah, it makes sense. Like basically an API, right? That just runs different.
Yeah. And so again, like we talked about this earlier, it's required that this show up reliably. So this is a totally different protocol. Use like TCP, and then because we want this to be reliable, and we don't care about if we drop a packet here or not.
Yeah. Also, maybe on that topic, you know how on Google Meets you can add like background, or I know like for example, even sometimes it happened to me that if I wave my hands, like some reaction would show up and stuff like this.
Yeah.
So how would this work? So I assume it's also, like MCU comes into play here, but yeah.
It could. So there's a couple things that could happen client side. So like maybe background is, I would say if I were building this, I would do it client side, because computers are powerful enough to do right. And so it would just be kind of right before the video is encoded. And I would encode it, and so the MCU just sees the same, like as if that came directly from the camera. There's another use case. I'm going to make use of this box here, like where you want to do like transcription. And so in that case, the transcription is just like another client, right? But it has a transcription service. So it would subscribe to the MCU video and audio, right? And then it can go to like email or Drive or whatever, like, right, as a box here.
Mhm. Okay, yeah, makes sense. But why would it need a video if like technically transcription on like is transcribing the text?
Yeah. So Google Meet, for example, has video recordings,
Mhm.
right? And so I would actually, yeah, you're right. So maybe, you
You
know,
mean like for the recording feature, then it would be like another service that technically like takes care of like storing like actually
yeah,
recording the video and then storing it. Okay.
correct. Yeah, I would do something like this. You know what I mean?
Okay, makes sense. Makes sense. Yeah. Okay. Yeah, that makes sense. Cool. Then what else do we have? I guess maybe so caption and summary generation. So transcribing the video, right? I guess in this case, it would just store, right, the transcription in like in a drive or somewhere. But if what if it's like real time,
Mm,
real time captions or something like this? So
yeah.
would it would it so that would be actually interesting, right? Because technically it's text, so it would need to be delivered like accurately, but
Yeah,
at the same time it relies on the audio that is
yeah,
UDP,
yeah.
right? So
So in that case, if we were adding that feature and I was like, Alexander, you're making this so complicated. I don't want to build all this. But if I had to, uh, if I was the engineer and I was like, we had to do this, we would make a like real time, like let's call it just AI, right?
Mhm,
Um, and probably what would happen is, this again would subscribe to the video, or maybe we need video for like emoji and or whatever, right? So this service here would get the video and audio, and then depending on what it's doing, if it's having to um, I bet this, like the thumbs up in Google Meets, there's no reason to re-encode that video, right? That could all be done client side. So I would just send that to the coordination server, right? Like real time transcription,
mhm,
um, emoji, like live emojis, and
mhm,
just say like, Victor stream has a thumbs up or whatever, right? And the coordination server would send like the like thumbs up data for like Victor or whatever, and then in the client, it could take the video stream and then superimpose the thumbs up and write it directly in the client. It just depends on like if you want to push that processing to all the clients, or if it's something that all the clients are going to see and care about. Like maybe it's more efficient to do it once. And that's either way. Like you can either do it at the MCU or
mhm.
at each client.
Yeah, makes sense. Cool. I think that's like mostly everything. Maybe in terms of like summary generation, I know there like currently, right, there are like a lot of AI tools that basically like take a meeting and condense it into a 1 minute summary. So I guess in this case it can be done with like given Gemini, right? If we take already like pre-built models, but if it's like you build it completely from scratch, then you would need to create your own
Yeah.
definition to handle it. But basically, so I'm just trying to think what could be like some interesting situations. So where for like summary generation, right? If it's a lecture, for example, right, and a professor is streaming, sorry, like is sharing their screen or whatever, right? So technically, what is displayed on the screen also matters. It's not just words. So
Mhm.
if you were to build a system where, it's not just, okay, take the transcription or whatever, like the captions, right, and then condense it and make a summary out of it. What if it also depends on what is actually displayed on the screen? So how could that be built?
Yeah, and it's a good question. I don't think it would be really part of, like, rarely would you want to do that real time, because I think it'd be really expensive.
Yeah.
Even like this transcription service, it's really just recording and sending it to Drive. Probably, I think if you've ever done a Google Meet transcription, it takes like 30 minutes later before you get the email that says it's available. I don't know if you've noticed that, right? So they're not actually doing that real time. So what ends up happening is that, this recording service sends and just literally just saves the video to Drive, right? And then you have this, this like transcription service that reads it and writes a text file basically back. Reads and writes it back to Drive. This is kind of like how it currently works in Meet. Like if I were to record a video and I get a recording later, I get an email that says, here's the video and here's the transcription, right? And so there's, when you do it out of band like this, there's no reason that it needs to be done live, right? Nobody's like refreshing Drive to see like the latest like transcription or whatever. But it's the same thing with like AI, right? Like some AI process has to watch this video, maybe watch video, multiple streams from different users, do whatever magic it does, and then output something. And that generally takes a lot of computing and time. And you may not have access to the GPUs in real time to support all that. So, I would say like, this type of, I don't know, batch AI service. Maybe we shouldn't have called this AI. So this is like the real time, like thumbs up service.
You
get really crazy with microservices. So like maybe we'd call this like the batch AI service. And again, it would just do the exact same thing, right? It would just read from Google Drive. Once the meeting is over, process, and then like, output somewhere, right?
Yeah.
Like summarization,
Yeah, makes sense. And then it can be sent to your email, I guess, as well, or something like this. Yeah, makes sense.
Yeah.
Cool. Yeah, I guess it's probably I don't think it's one of the Google Meet features, so I just was wondering like how it could be potentially done. A little bit out of the scope.
Well, you see you see these third-party services join Meet sometimes. Like somebody will join.
Oh,
Meet, and that's basically what they're doing, right? So like, they're just another client, AI client, right? And so they just do
interesting.
They do their own capture, right? And so then, they're storing it in their version of, whatever backend they're storing it in, right? And then it does this like, AI processing, like independently of Google, right? That's just like, there's a dozen of these companies now that like join your meetings and take your notes and give you summarizations.
Yeah, makes sense. Cool. I think that's mostly it for today, right? I guess to summarize all of the different use cases is you have like 3 pages. So the first one we briefly discussed, like when you have just a couple of users and you have this mesh network, as you said, right? And then the second and the third diagrams are more applicable to actually like streaming for multiple users. And so makes sense. Also, maybe if we'll share like those diagrams in the comments, ideally. So we'll probably like take a screenshot or something.
Yeah. Let me clean them up.
Yeah, sounds good.
We're going in a rush. Clean them up, make a little bit of sense, and then yeah,
Yeah,
I'm happy to share them in the comments.
perfect. Thank you. Great, but I think so. Thank you so much for to everyone for joining us, and thank you so much, Victor, for sharing your expertise and knowledge, and going through so many different use cases and scenarios. And so appreciate your time. I hope to see everyone again. If you're in the Waterloo region, please hope to see you at our Dev Fest. So I just shared again the link to the event in the chat, and hope everyone has a great weekend. And yeah, we'll see you later. So thank you so much.
Thanks.
Bye bye.